which is not just a little blip on the radar. Let me fire up what we were doing last time. You guys, the quizzes you did last time, I don't have yet because Amber wants to grade those because, like I said, she gets paid hourly to do that. She didn't pick them up yet. I figured, what the hell? Go for it, right? Go for it. But I do need this, and I do need this. So last time, what you did on the quizzes was you did your first bit of inferential stat, where you were rolling dice and trying to figure out what the average die rolls were based off your samples. And the very last thing we did was we had you guys put some beautiful curves on the board, which I took a picture of, probably deleted off the camera. I threw my recycle bin and try to find it. But what were some neat things you noticed about those sampling distributions on the board once we had them all on the board yesterday? They all turned bell curves, even though the distributions themselves generally didn't look bell-shaped at all, except for the red one. The red one did. But orange, totally not. Green, yellow, highly skewed. Blue, highly skewed. All of the skew, we'll deal with your skew too today, for sure, Nick. You mentioned a skew earlier, I remember that from Monday. Highly skewed distributions, upon sampling, the skew disappeared and was replaced with bell. That was very interesting, yes? Mm-hmm. And because they were bell-shaped, do you remember what the highest point of the bell was in all of those sampling distributions? It's okay if you don't.
It was mu.
But it was mu. It was mu. We're going to look at that again today. The highest point of each of those bells, almost like a target, was saying, hey, you, researcher, look at the high point of this curve. What you're looking for is most likely right here. Why do we care about that?
Because that means that you can do random sampling and represent the population.
Because that means you can do random sampling and get after what you're after. Good. So the bell curves show up, which is great, because then we can actually do stuff with the bell curves game. And then we can do the random sampling and get accuracy. We get accuracy by actually getting the high point of the bell curve being what we're looking at. But the problem was, that was just the high point of the bell curve. There was still a spread to the bell curve. And that was a problem we didn't leave resolved, in particular the skew. So what I did was, I drew up this, which I hopefully will help us. I'm going to have to shrink it down so it fits better. What I did was, I used Excel to simulate these dice. Now, I only did the blue dice, so anybody that used green, orange, yellow, or red, not that I'm ignoring your dice, but this spreadsheet already runs pretty slowly with one set of dice. If I had all 5, it would be intolerably slow. So what I did was, I mathematically simulated the blue dice. So what I did was, I blew out the dice. That's what the blue dice looked like. Anybody that was rolling the blue dice, if you blew them out, they had 1, 2, and then a bunch of 6s and 5s. So if you remember, this is what the distribution looks like. Smaller so you can see it. That's what the distribution looks like. Now the tricky part about this is, that isn't the actual distribution. When I press F9, I'm actually rolling these dice. Do you see how that distribution is changing? That's because we're not actually, it didn't do what, and Tim's saying, it's not changing that much. Good. It's not. That's 4,000 dice rolls. So it's keeping track of 4,000 rolls of those tricky blue dice. And the sums are over here, as you might see. So in the first sample, there's a 12, 6, and 11, 11, 7, 11, and 12. And it's plotting those over here. Now, because those numbers get a little unbearable, there's 4,000 of them, instead of doing it as a frequency, I did it as a relative frequency or a probability. So 20%, 15%, 10%, 5%, which correlates to 1 through 36. But this is easier to deal with because the numbers just get too big. I mean, you really want to have 4,000 on the axis? Probably not. So no, we don't. But do you notice when you compare this to PowerPoint with the blue distribution on it, which is right here? Look at that one. That is the actual one you guys did in class by counting. Here is a simulation of the exact same distribution. And notice it is wiggling. It's doing a little bit of a dance. But it's never dancing far from what it's actually supposed to be. And that's the beauty of simulation. That's the beauty of theoretical versus empirical. Theoretical is fine when you can actually count all the sides, but as we learned yesterday, you can't count all the sides. The problem with this is still problematic because those particular sums that are being gotten are actually drawing from the population that I know back here on sheet number 1. So I said, let's be more realistic. Let's be researchers. Let's replicate what you guys did in class yesterday. So here, I did the exact same thing, sample 1. And what you'll notice out here, it looks a little terrifying. But what I actually did was, that command up there in that formula bar basically says generate 2 random numbers, and then go back and look at the distribution of the dice and roll them. So it seems terrifying, and don't worry about it, you're not responsible for it. But every time I press F9, it's actually generating a roll of those blue dice. Now, what shape are you seeing in front of you right now? Yes. It's actually more bell-like than the ones you got in class. Why? Why is this one more bell-like? I got 1,000 trials. You guys had at best 75 yesterday, right? Because our classes aren't that big. I had you guys roll, each group roll 25 or 100 times to make 25 samples of size 4. This is rolling 1,000 samples of size. You can see them just roll down. There they are. This is the beauty of Excel, that it can actually do this and not get tired. So every time I press F9, that's 1,000 more samples, 1,000 more samples, 1,000 more. And what do you notice about those? The bells are dancing around, but what is staying? Well, the bell's staying the same. What else is staying the same on average? Say that again, nice and loud. The value of that middle of the curve is basically dancing right around here. So the question, where's mu? Now you know what mu was. If you don't, I forgot 2 actually. It's 8.1666666. But in reality, we're not going to know that. Does the curve tell us where it is roughly?
Yes.
Yes, it tells us it's in, on average, the highest bar. Look at that, 8 to 8.5. That's where 8.2 is. Now, sometimes it misses. Sometimes it misses. There, it missed on that one. But on average, it's not missing. But here's a bigger problem I have. On average, it's hitting, so we're back to what Madeline said about, as researchers, we're targeting on accuracy fairly on average. The problem is, what if my sample comes back? There's 1,000 samples here, right? What if my sample is that one? Then I've missed it. That can happen. It's an outlier, yeah? It is an outlier. But it can happen that I actually end up out here. It's more likely that I end up in here, but what happens if I end up out here? Well, it would be nice if that wasn't even a possibility. But that's like just remove that. You can't just remove it. Or can you? How could we remove the possibility of having an average that would be this far off? What do you think?
Shrink this.
Say that again. Say that again. I heard shrink the...
Deviation.
Good! How can we do that legitimately? I love that, Renee. Good! Renee's got an idea. If we shrink the standard deviation down, that'll take care of the bell curve will then collapse this way. And if it collapses this way, where's this going to have to go?
Up.
It's going to have to go up because the area is still 100%. So if I shrink the curve this way, kind of like Play-Doh, or it's going to have to go like that. I'm envisioning my son, that Play-Doh thing he has where he squeezes it and shoots out the end. It's going to have to do that. If I squeeze it in, it's going to have to go that way, which actually would be fantastic. Because if it went this way in the middle, that would mean we're even more likely to trap where the average is. How do we do it legally? Let me ask a question. Look at this out here. There was a sample in here that had an average between 11.5 and 12. That's ridiculous, isn't it?
Mm-hmm.
It's also very unusual. We also had some averages between 2 and 2.5 and 2.5 and 3. Very unusual. What has to happen in those cases when we have either averages that are that low or that high? What has to happen each time we roll the dice? They have to clump around the small numbers, right? So in order to average 2 or 3, for example, we have to keep rolling 2s and 3s. How likely is that?
Very good.
Not very. Remember the distribution? Remember the distribution? The likelihood, oops, back to here. The likelihood of rolling a 2 is about 2%. So in order to roll a 2 4 times in a row, that's like 2% to the 4th power, which is really, really small. What would be even smaller? 2% to the 1,000th power, or I wasn't even going to go that high originally, I was going to say like 5th power. So suppose somebody has rolled a sum of 2 4 times in a row. Give them those dice again and say, dare you to do it again. Because the chance of it happening again is still 2%. The chance of it not happening again is 98%. So in other words, I think we may have an idea of how to get rid of how to make the standard deviation shrink. And what's that? Hand them the dice again, which would be equivalent to running what? Uh-huh. But I say, let's bump the sample size up too. Instead of doing 4, let's do it 9 times. Why 9? I'll come back to that. Okay, so here is the exact same experiment. This is the exact same experiment you guys did in class yesterday. But instead of saying roll the dice 4 times an average, I rolled 9 times and averaged them. Now, what do you notice? It's a bell curve, centered on the average still, but what also happened? Look, remember that there was 11s over here before? The 11s aren't there anymore. Let's see if we can get them.
Okay, but I thought it was 8.2 for.
What's that?
Was
Yeah,
the
it slid
new-
our average and our mean, right?
Hold tight, hold tight. Look at these two bars dancing back and forth, right? There's a dance back and forth. 8.2 is close to the top of this one and the bottom of this one. So it's going to flip-flop back and forth. On average, you're going to see more of these. Hold that thought. I added a sheet last night because of what Danny said in class, which will address that perfectly. Hold that thought though, because it's closer to one side of the bar than the other. This is where we're going to have to get micro, and this is why I had to add the sheet to it. We have to analyze it even more micro. Yes, John. So it's going to, like right now, it missed it completely on this side. But on average, that's not going to happen. On average, it's going to flip-flop back and forth here with slightly more here. Hold that thought, though. Hold that thought. Okay, here we go. Notice, every once in a while, this guy pops up. I saw one right there a minute ago, yeah? Watch it right there. Oh, crap, I thought I just saw it. Oh, there it was. Now, how about down here? Are we seeing these guys?
No.
We're not seeing those guys at all. Now, the reason for that, again, is the original distribution. It's pretty possible to get an 11, but it's almost impossible to get a 2. So we should be seeing more 11s than 2s, but they're both becoming exceedingly rare because you have to keep doing it. It's like going into the store with Max and saying, Max, just keep buying little birds and betting on not getting a rooster. The more you buy, the better a chance one of them's going to come out a rooster. That's the idea. Okay? So, Renee, I like your idea. It's very, very nice. Can we make it even better? Yes, even more. Same experiment, but now we've done it with 16 rolls instead of 9. Now notice the similarities between this experiment and 9 and 4. What are the similarities between all these? Similarities? All bell curves? Other similarities?
All highest around 8.
Uh-huh, you're trapping that average. Yes, you're trapping that average. Good. Differences.
The spread.
The spread is decreasing, yes? The spread is decreasing. It's much, look, here's 11 now. We're not seeing 11. We're definitely not seeing these guys. These outliers are becoming more and more rare with each. Here's 25. Here's 25. Okay? And finally, here's 100. Now this looks almost ridiculous. Almost 60% of the data is falling in the 8 to 8.5 bar. And this is where, Danny, you made me think of it yesterday when you said, wait a minute, with your red curve on the board, you said, it doesn't really look like a bell curve anymore because there's so few bars. So here's what I did. When I got to this sheet, notice how everything essentially is between 7 and 9, well, 7 and 9.5 now. Like if I keep pressing F9, you're really not seeing a whole lot outside of that. You're not seeing any 6.5s or 7s, and you're not seeing any 9.5s or 10s. So what I did was, I went back in, and see if you understand what I did right here. This range on the horizontal axis represents the exact same range on the previous one that was between 6 and 9. But I took off all the bars that were meaningless, and I broke up the bins. As opposed to being 1/2 of a unit apart, now they're 1/10 of a unit apart. Because what I wanted to show you was the bell curve is in there. It's just that when you're only binned down this much, it doesn't look very bell-like. But when you take a finer tooth comb to look at it, look at that. That looks identical to the first one, right? Except now your bins are only 1/10 of a unit apart. And if we went to even higher, I tried to go even higher. I tried to go to 10,000. And that's when I hit F9, and Excel went, and then like 16 seconds later it went, and I'm like, that will piss them off in class. They won't like that very much. So I stopped at 100. But thank you, Danny, for saying that yesterday, because I never thought about that. Yeah, the previous one to me looks like a bell curve. But to you guys, you're like, it looks like 3 bars, one of which is the tallest, one of which is... And John, going back to you and Madeline's point, notice how this bar is taller than this one. Okay, notice that, guys? And it stays that way. It stays that way.
So it's pulling it to the left.
Yes, the skew on the average being 8.2 is closer to this side than this one. So you're getting more of these than these. It's not perfectly symmetric. But the overall skew of the distribution basically eradicates as the sample size gets larger. So thank you for all those points you guys brought up. So, this might be a little bit of a headache to look at. But, what you're looking at right here is all 5 of those experiments at once. So what I did was I pulled the data from the first sheets. Samples of size 4, 9, 16, 25, and 100.
pretty impressive.
And I plotted them down here. This was fun to look at them once. Yeah, this is fun to look at them once. And statisticians will always tell you never do a 3D histogram. Know what I say to that? To hell with that. This is the perfect place for a 3D histogram. Look at this. See what's happening? It's totally rad, isn't it? And what are you noticing? What are you noticing? What are you noticing? What are you noticing?
8 to 8.5 is always the highest.
That average is right there. On average, the highest bar of every single one. So you know it's within 8 and 8.5. So you got a little tiny margin of error on that's fantastic. Now, the overall curves, what happens as we go front to back with this middle bar?
They go up.
Why is it going up again?
Play-Doh.
Because the Play-Doh! Because Renee's standard error has been taken care of. We've smushed in the curves, and if we bring them in this way, the area has to go somewhere, and the only place for it to go is up into the middle. Fair enough? Good. Danny?
Okay, so you're getting rid of your variance, which is the point of your data, is to show you the variance and to show you what's wrong with your population or what's going on with
How variant it is. Not so much
Yeah.
wrong, but how it deviates.
Yeah, and so if that's what you're looking at for your, like, value, what you're trying
Getting rid of it seems like a bad thing.
Exactly.
Hold that thought. You hear what Danny just said? It's awesome. She's like, you're getting rid of your variance, so that seems like a bad thing because that's what you're trying to measure. Let me phrase it a different way that might make it clearer for you. When I asked originally, why were we happy about the high point of the curve being around the average, the response was, what? Why are we happy about that?
Because it's the sample is representative of the population.
On average, we're catching the average. I'm using the word twice there now. On average, we're catching the average in the middle of our sample. But the problem is we're going to be off by a certain amount on that average. So don't confuse the variance in the population with the deviation in our sample. The variance in the population is there, we're never going to know what it is. The variance in our sample, though, I want to make that as small as possible. If you're reading a poll, and Gallup said the margin of error on this poll is 4%, but the margin of error on this poll is 1%, which one seems more statistically strong? The one that has the 1% margin of error, because what you've done is you've shrunken down the curve to this, so your offness is less. So when we're talking about variance here, the offness is what we're minimizing. So it's not a bad thing, it's actually a really good thing. More on that to come. It's called precision versus accuracy. Go ahead, John.
So the 2s and 3s and 11s and 12s, they happen so rarely that they
basically disappear.
Right.
Because essentially the probability is 0. I always pray for one to pop up, but I'm usually pressing F9 so fast if it does, I'll miss it. It has to happen eventually. If you roll a pair of dice long enough, it's a Shakespeare monkey prop, you've heard this, right? Take an infinite number of monkeys, give each one a typewriter, and let them type forever. Eventually, you'll get the complete works of William Shakespeare. Because they're slamming away randomly at a typewriter. Because randomness says, at some point, to be or not to be will pop up, along with every other line, herefore art thou, whatever the hell Shakespeare, I don't know, I've read Shakespeare in 25 years, but that's the idea. If I roll these dice randomly long enough, I will get 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. What the hell's happening? 2, 2. It's got to happen somewhere. But the thing is, it happens so rarely that unless you're looking for it at that moment, you might not see it go by. Good. So essentially, they're 0. That's what all these flat parts are over here, the zeros. Good? Excellent. Now, I want to get a little bit more refined. Take a look. I've collected all the data into a chart up here. Here's the actual population that we know nothing about, right? The problem is we never know what these values are. But we know, because of experimentation, that mu is 8.2-ish, and the standard deviation of the population, which is not changing, is 2.7-ish. We know that from what we did in class yesterday. Okay, fair enough? Good, good. Here's a sample size 4, 9, 16, 25, which seems like very strange numbers, yeah? Weird numbers for me to use. We'll come back to that momentarily. Every time I press F9, what I'm doing, having Excel do, is it's going back into all those simulation sheets, and it's rolling the dice 4,000 more times. This is the average of all of the sample averages in each sheet. So in other words, in the sheet of sample size 4, which is the one down here, it's averaging all 1,000 X bars, and it comes out to be 8.16 on average. It's going back and averaging all 1,000 X bars in the n equals 9, all 1,000 in n equals 16, all 1,000, all 1,000. What do you notice about these? What do you notice about that?
Really close.
They're very close, and very close to what?
To
Boom! We already figured that out, yeah?
Yeah.
These guys are exceptionally close to mu. But that was indicated by the curves, yeah? The curve being highest in the middle. So on average, we're targeting. Again, we get happy about this. Now sometimes they're off by 8.2, 7.99. They get off. But on average, they're not off. On average, they're dead on. How about these? Look at these numbers over here. Are those numbers congruent with what Renee talked about 10 minutes ago?
Yeah.
Of course. What's happening to the standard deviations? On average,
They're going down.
they're going down. Now here's where I want to pick your guys' brains. They're going down predictably. See if you can figure out how. They're going down, yes. But just knowing they're going down doesn't help us design studies to say, for example, I want to be off by no more than 3%. You could say I don't want to be off, but that doesn't help statisticians. Statisticians need to know how much. Andrea, what are you
But
saying?
isn't it going off depending on the sample size?
Yes, and that's what I want you to figure out right now.
Anyway?
How big is 1.32 compared to 2.7-ish?
It's about a third.
It's about a third, okay? Let's reload it again. 1.37, 1.36, 1.32, 1.34. Is it staying roughly consistent?
Yeah.
Okay. How about 0.86 with 2.7? And make these nice numbers. Call it 0.9 and 2.7. That's about a third, yeah? 0.9 and 2. So this is more like a half, yeah?
Yeah.
That's more like a half, 1.3 to 2.6. So that's like a half. That's like a third. What's this one? Ish. Ballpark. That compared to that. You know what? Let's do this. Let's do this. We got Excel, right? Let's explore. Let's do equals that divided by that. Okay? Oops, it didn't like that. C. C4.
Because it says ish.
Oh, shize it does. 2 point, thank you, it's next. Thank you, whoever said that. 2, there we go, 2. Now what I can do is I can do that all the way down for all of them. Okay, so here we go.
Oh, that's.
There we go. So look how it's hovering right around 2. This one's hovering right around 3. This one's hovering right around. This one's hovering right around. What's this one hovering right around? Are you seeing now why I picked the sample sizes I picked? How are these numbers related to these sample sizes? This is about 2, that's about 3, that's about 4, that's about 5, that's about 10. They're the square root of the sample size, predictably. What? I wait till the last day and then throw a square root at you. So, Renee, yes, the sample standard deviations go down, but they go down predictably as a function of the sample size. What? That means if we let our sample sizes go off to infinity, they shrink to 0, but we don't have to get to 0. Being 1% or 2% off is usually enough, and what's amazing, and we'll study this in 244 at length, is that you don't have to get a whole huge sample to get down to 1 and 2%. Sometimes 4,000 will do it. I mean, you might think that 100, okay, 100 is 1/10. That means that you have to get to 10,000 to be 1/100, and it is. That's why I was trying to get to 10,000. Because 10,000, this would have gone to 100, but it wasn't working. It was too much computation for Excel to do. So what I want to do is summarize all this. Yes, we have to do this before 11. I want to summarize everything you guys came up with between yesterday and today. Here we go. You ready? And this is called Be Mighty, Be Beautiful, Be Gorgeous. Central limit theorem. You don't have to write this down if you don't want to. This will all be posted. It already is posted actually on your schedule page, and I'll have it all posted for you as well. So this is the whole point of inferential stat. You want to study a population, but you have no idea what its average is, or let alone its standard deviation. I mean, they're unknown. You don't know what mu and sigma are. So the idea is to go do a study, grab data, study the sample, and say, okay, here's what my sample data shows. Can I glean anything from that and then reverse engineer the population from that? Which is what Madeline mentioned about 30 minutes ago. And the answer is yes, because of this bad boy. Yes. So the first thing you do is you go out and grab some data. I call it size n. This is kind of like your nth row, Madeline, which we'll talk about at break for sure.
Thank you.
So, and n is an unknown. I mean, you're going to fix the sample size, and it can vary. It can be 100, it can be 1,000, it can be 2,000, 2,500. Some samples have hundreds of thousands of trials in them. Excel right now has 1,000. Fair enough? Okay, good. Good, here we go. The first thing, I made up a symbol here, I hope you don't mind. The first thing that you get is you get a bell curve. Now, I'm using a phrase we first learned on Monday, which is called a sampling distribution. Everything you were just looking at that was bell-shaped on that Excel spreadsheet was a sampling distribution. And the reason it's called that is because what you're graphing are the averages of the samples. Hence, a sampling distribution of the averages. So it's not the population's distribution, which you're never going to know. So in other words, yeah, you're going to get a bell from your samples. The population could have any shape at all. Any shape, and you'll never know that without more study. But the sample itself is going to be bell-shaped. Yay, that's yay number one. Because now we get all those cool percentages. We get the 68, we get the 95, we get the 99. Yay, that's wonderful. That's wonderful. We got just a normal program, all kinds of great crap we can do. Now, this is a symbol I made up. The average, okay, there's the sample average, X bar. The average of all the sample averages, which I've cleverly called X double bar. Clever. Is gonna be mu. Is gonna be mu. Now this, I can't emphasize this strongly enough. That's an equal sign. Not a squiggly equal sign, that's an equal sign. Now you gotta realize, it wasn't equal on the spreadsheet, was it? When we were doing the F9, it was bouncing around. It wasn't going exactly to 8.1666666. It was bouncing 8.12, 8.22. But on average, if you draw every single possible random sample of that size, we weren't. We were drawing 1,000 random samples. There are more out there that I wasn't getting. But still, even though I was only getting 1,000 of them, I got enough to actually see that it was damn close. But that's mathematically equal. If you're interested in why, which I don't expect you to be, I put a proof on the website for you. But I don't expect you to ever read. Unless you're having trouble sleeping, in which case, go ahead and read that. Renee, go.
What are you assuming though that it's going to be normal?
Oh, I'm not assuming anything. I'm saying it's going to be. That's why it's the central limit theorem. The theorem states it will be normal. Now, there's a proof of that too if you're interested. There is. It's heavily dependent on calculus, unfortunately. But there's a proof of why the bell curve is there. If you're interested, just check the original page and just scroll down to the bottom until you see it. My friend, thank you for asking.
Can you tell me once again what you call your new?
Oh, sure. So that is your sample's average.
All right.
This is the average of all such sample averages. So if you drew every single possible sample of size n, and averaged all those averages, it's an average of averages.
So that was the last page you showed. With those
Pretty much. That was my approximation of
Okay.
that, on that last page. Does it ish make sense?
Yes.
Yeah.
Good. There's your yay. There's your yay squared. We're going to have 5 such yays by the end of this, because there's a lot of goodness. That's why it's the mighty central limit theorem. Now, the problem, of course, as we discovered, is although this is true, and this is mathematically true, you don't get X double bar in your study. You get X single bar. Yeah? And that's the problem. That's the problem with the central limit theorem, is that X single bar does not equal mu. You get one. You don't get all of them, which is kind of unfortunate, but it's also kind of realistic. If you could get all of them, that would
You
mean
wouldn't need to
you
sample.
wouldn't need statistics, because you could get the entire population, right? So the mathematics of the central limit theorem says X double bar equals mu. The reality of life says, yes, but we don't live forever nor have infinite funding, so we get one sample. Sometimes we get more than one, but we definitely don't get all of the possible samples. So that's the reality. This is the reality check, if you will. But we can use the on average we're hitting it part and tie it in with what Renee talked about shrinking down. So here, and this might look a little weird, but you guys figured this out already. We're going to introduce a term. For those of you not taking 244, this is the only time you're about to deal with this. Unless you take other statistics later. For those of you taking 244, we're dealing with this every single day of 244. It's called the standard error of the mean, which a lot of journals just call SE for standard error. What that means is, it's a measured standard deviation of a sample. Now the trick is, why not just call it standard deviation? Why don't we just call it little s?
Because it's just that sample?
Because, well, that's actually should be called little s, because it's just that sample. The trick here is, this is the adjustment you have to make when you're approximating not just the sample, but the entire
average of all
population.
of them?
Yes. And the thing is, the more data you draw, the less variant your sample should be. And that's where this comes in. Remember the square root of n that you guys came up with? Square root of 2, or square root of 4, square root of 9, square root of 16? Remember how it was shrinking by a factor of that?
Yeah.
The standard error in your sample is going to shrink whatever sigma is, which we don't know, is going to be shrunken by a factor of the square root of n. What? That's like a head-popping moment. When something this crazily, seemingly tangential locks down to a beautiful mathematical construct like that. That to me, was the mind-blowing moment. Again, it's in that proof if you want to see it. So, I want you to hear what Madeline just said, though, because it's important. There is a standard deviation. I was actually calling those S's. Because each one of the samples has a standard deviation. Each one of the samples does. But when you put all the samples together and graph them on the graph like we did, the standard deviation of that is called the standard error. So if you will, if you think about it like that, it's kind of like a standard deviation of standard deviations. Just like X double bar was an average of averages. What you're looking at is the spread of, I know, it's a little bit mind-bending, but there's not much math involved, which is the beautiful part. There's not a whole lot of math involved. And all you've got to do is realize that whatever sigma is going to be divided by root of the sample size. If the sample size is 100, you're dividing by 10.
Right.
It's pretty much, it's way more, it's worse in words than it is in practice, if that makes sense. We'll come back to some examples of this in a minute. Now, this might make it a little bit worse. But you're going to recognize some of this. You're going to recognize some of this. Angie, go get your vomit. I'm sorry. Apologies. On average, see if this makes sense. What you're looking for, mu, which you'll never know. He's out there, or she's out. It's out there, but you're never going to know what it is. But on average, it's going to be within two standard errors, or standard deviations, but I'm going to call it standard errors just because that's what we're doing because we're sampling. So see if you can see how this ties to exactly something you already know. What you're looking for should be x bar minus 2 of those things to x bar plus 2 of those things. Does that ring a bell?
Yes.
Yes! That's 2 standard deviations. That's what cuts off the outliers.
Yeah.
That's all that says. So what I'm saying is, yeah, we've introduced a new term called standard error, but it slides right in with everything else. It's like Legos. It's like you now have a yellow brick that fits exactly where the green brick used to fit.
Yeah.
It's still Legos. It still works. It's not like you have to invent a new brick. No, it still fits. So 95% of the sample averages you get are going to be within 2 standard errors of the mean. Yay! That's fantastic. And the smaller the standard error is, the closer that 95% is going to be. That's also fantastic. Because that means you can be off, but you're going to be off less as your samples go up. And that's the whole point of what you said 45 minutes ago, Madeline, about the idea of sampling. You want to get the idea of where the center is, and the closer you can get the center, the better it's going to be. Yes. Believable? Mm-hmm. Believable? Mm-hmm. Good. Okay. Now, this is a little bit wordy, so I have some visuals to go with it. Read that first.
Yeah.
And this is a yay to the 4th, just because happy.
You know, the first couple you put on the outside of the parentheses, so that...
Are you kidding me?
I'm not.
I have to fix that. As a German, that drives me insane.
Yeah, your third one was done that way too.
Oh, damn it. I'll fix that one later.
Sorry.
Oh, thank you for telling me. As a German, I hate that consistency. Yeah. Does this make sense? If it doesn't, I have some images to go with it. Because I'm throwing a word precision out there. I'm putting the word precision out there. It's precision. Is the first part okay? Since the standard error is inversely proportional to the sample size.
Yes.
That means as one goes up,
The other one gets smaller.
the other one goes down. Which hopefully makes sense. As the sample size goes up, Renee told us the standard error was going to shrink, and it did. Predictably, as the square root of the sample size, it shrinks. Good. What does that have to do with precision? Well, there are 2 words I've thrown around today. John, you actually helped me with one of them earlier. There's the word accuracy and there's the word precision, both of which have, and I think you may have learned these in other classes at COCC or even before COCC. They both play into the world of statistics. Accuracy measures one thing and precision measures something else. And I think the best way to kind of draw a parallel to these is to show you 4 pictures. Suppose, forget statistics for a minute and pretend we're standing out in a target range with our shotguns.
I want to go with that guy.
Well, definitely. I mean, if the goal is to shoot for the bullseye in the middle of the targets, clearly this is what we want. Because this gun, or the shooter of the gun, or both, have both accuracy and precision. So what is accuracy based on this image here? If you're accurate, what are you doing?
You're hitting the target.
You're hitting the bullseye. So good, and look around at the other targets. Does any other targets have accuracy as well?
That is
Bottom
precise but not accurate.
So but as far as accuracy, who's got accuracy? Andrew, this guy has accuracy, yes?
Yeah.
But this guy lacks? Good, so precision is a measure of variance, so to speak, where accuracy is a measure of middle. So accuracy is, are you hitting the middle of what you're trying to hit? And precision is, how well are you hitting the middle?
Sean, is there anything to do with, there's another thing I'm noticing, those over there, the person with the shotgun standing closer to the person.
No, assume all four of these are at the same distance.
Well, yeah, but they wouldn't.
They would if the precision was different.
That doesn't come into, because those are tighter groupings, that would signify that the shotgun was close.
Oh, I see what you're
I didn't
saying.
know if that was something you were
I don't know
trying
anything
to
about
bring
guns,
out or
Tim.
what.
God bless us. I'm trying to come up with a non-statistical example.
Yes,
It's not a
I
shotgun.
didn't know if you were going to bring
It's
that
not a
up.
That's a good point.
It's not
That's
a
a-
shotgun.
It's not a shotgun. It's 20 shots of a normal
Okay,
gun.
okay, okay.
There we go. Thank you, Jim. I'm trying to be all non-statistical, and you gotta call me on it.
60 yards.
It's not a shotgun. Thank you, Shelby and Danny, for saving my bacon on this one. And you can't talk the rest of the day.
Precision varies
Measures variance with, and that's in any context, how well you're hitting what you're trying to hit. So in other words, these people shooting the non-shotgun gun are doing a pretty good job of hitting the bullseye here and here. Here and here, there's a problem with where they're aiming the gun. It could be that the scope itself is miscalibrated, or it could be that they don't know what they're doing. So this and this have good accuracy because we're hitting center. This one's also got good precision because more of them are hitting closer to the center. Is that believable? Mm-hmm. Up here, these guys both have low accuracy. What does this one also have?
No precision.
Low precision. Whereas this one's got terrible accuracy and high precision. So, and if you're talking about like I'm assuming with a gun standpoint, this person most likely thinks they're shooting at this, but for whatever reason something's calibrated wrong. And if you could just adjust the scope somehow, maybe they would actually be hitting the target then perfectly. Whereas this one could be just like this one, with the same scope reason. So you see the difference between accuracy and precision? Accuracy is how well do you hit what you're trying to hit. So in statistics, it's how well are we catching what we're trying to study. And the beautiful thing about the central limit theorem is it guarantees that we're catching what we're trying to catch because all those bell curves are centered on the average. So we are promised accuracy. Yay. That's fantastic. And the precision only gets better
With the higher sample
with a higher sample size. So you guaranteed accuracy, and you're actually guaranteed precision off the bat too with a small sample, aren't you? Because there's variance in the population. As soon as you start sampling, that root n starts kicking in. I mean, suppose you only sample 4. Now you're twice as precise because you're dividing by 2. So the variance shrinks down by a half, and then a third, and then a fourth, and then a fifth, and the next thing you know, you're dividing by 15 and 20 and 30, and you're shrinking. That bell curve is getting taller and taller, and you're feeling better and better. Please.
Okay, so I'm just trying to make sure I understand the
Yes.
difference. So if you're hitting the middle, you have accuracy.
Yes.
But if your stuff's just all over the place.
That's low precision. High precision, tightly clustered together. Low precision, opened up more like that.
Okay.
So the idea is we are guaranteed So in other words, the central limit theorem says this will never happen to us. Statistically, we can never have this happen because we're going to be hitting the middle on average. That was step 2, I think, in the central limit theorem. On average, we hit the middle. This will happen to us. That's a smaller sample size, and this is a larger sample size. Yeah. Essentially, mathematically, to bring it back to statistics. Cool? Make sense? Yeah. This is fascinating. Absolutely fascinating. So, this is a lie I've heard for years. For some reason, textbooks seem to think that 30 is an acceptable minimal sample size. There is no such thing as an acceptable minimal sample size. You can do amazing statistics on very, very small, even smaller than 30. Now, we'll study this at length in 244, right off the bat in 244 for that matter. There's absolutely zero need at all to limit it to 30, and I'll talk about more of that why. But the basic idea is just the larger you get, the better your precision. So there's no need for a huge sample. I mean, you saw what happened with 4. With 4, the bell curve kicked in with our die rolls. But nobody ever does samples with size 4. They do samples with size 1,000 or 2,000 or something along those lines. But you don't need that. You don't need humongous samples. 105 today, somebody actually said, what were we talking about? I'm talking about results we got in class on die rolls. And we did 250 trials. It's like, well, that's nowhere near enough. You'd have to do it like 1 million or 2 million times. And I'm like, well, it depends on how precise you want to be. And it was like, I don't get that. Good, you shouldn't get that in 105. We're not there yet. We're not ready for that. You have to understand the bell curve, understand what variances and things like
Doesn't
that.
it make sense to do like a variable of 10, like to 100 or 1,000?
And just keep seeing what happens.
Yeah, because your percentages are right there for you.
Exactly, and that's what we're going to have them do on their last exam. We're going to have them come in and generate random numbers with their TI and just keep adding to it, keep adding to it, keep adding to it. And then they're going to see what's going to happen is those intervals are going to shrink down. I won't call them confidence intervals, I won't call it standard error, I won't call it mu. But they'll see that their estimates are getting better. And this is the whole point. You got it, John. That's actually one of the things I got to talking about while I was late today. Getting to class, I ran into a colleague talking about a better way to teach statistics is by having you guys do exactly what we did on Monday, which is give you a bunch of dice and start rolling them and see what happens. Rather than, the traditional way is just to give you these 6 points on Monday. Okay, great, have a nice day, bye. A better way is to see what the hell happens. See why it's happening. I mean, maybe not why. Why is the proof? Why is what's buried on the enrichment page? But at least see that it's happening. And if you want more proof, I got mathematical proof housed online for you. But at least you can see, like, there's a motivation for it. Like, oh God, oh God. Like Andre, when you were like, whoa, at that one point. Me too. Trust me, every time I do it, I'm like, holy crap, there it is again. It blows my freaking mind every time. It's cool. It's the dance of mathematics. So, there it is. There it is. That's the whole shebang. I did include some of this on your take-home exam. It involves a spreadsheet, and it involves randomly. It's kind of like what I did up here with Excel, but I made a spreadsheet for you guys to play with Excel, and it involves terms like standard error and things like that. So it's already posted for you guys. When's your guys' exam? Is it Wednesday? Wednesday.
15.
I'm going to leave the central limit theorem stuff off the in-class exam, I think, and the reason is because this is our last class. So if I was to assign homework for it, we couldn't go over it before your exam. I mean, we could if I was a bastard. We could come in on the day of the exam and go over homework for half an hour and then give you the exam. But that's not cool. That's not cool at all. So I think I'll just leave the central limit theorem stuff on the outer class. There is a component to that. That way you have plenty of time to look through it. You can look at the homework and see how it relates. It relates perfectly one-to-one almost. But for the in-class exam, we'll just keep it binomial and normal between those two ideas. Cool. That's 243, friends. That is it, babies. You guys are awesome. Total rock stars.
Thank you.
Even you with the gun comments, and that's all right. That was fantastic. Very good point, by the way.
Well, you know, I was thinking too, I was trying to be intelligent about this or whatever.
You don't have to try just
Too, as far as like accuracy, I was thinking about how taking sample sizes or whatever, where if you're standing further apart, you're going to have less accuracy. So if you're
Necessarily.
closer, I don't know. I was trying-
All things being equal, you could also be measuring a different kind of casing. Maybe a different design of casing presents a larger
It's
shot.
a bow, not a gun.
I can't get the shotgun out of my head.
I shouldn't even be using
It's just
arrows.
arrows. Robin Hood.
I think I shot guns once in my life.
Robin Hood.
Robin Hood?
It's arrows.
It's arrows! Beautiful! Forget the guns. We'll put a little picture of a bow and arrow. Not to mention the guns. Apparently guns.
Okay.
Yeah, cool? So that's it. We can be done. I can stick around if you guys want to ask questions. That's it. That's it. There's no need to do anything else. Our brains are full. Thank you guys. You guys are awesome. Danny, well,